All right. Now to our sets of numbers. Again, really quick because this is just review and we already know all of these, but reminders. Our natural is the most restrictive set, and that is going to be our counting numbers. Abbreviated N, it is our counting numbers starting at 1. Whole numbers, all that changes when we move up to whole numbers is that we add 0. Abbreviated W, 0, and the counting numbers. If you got to the warm-up today and you realized that you couldn't remember what whole numbers were, this might be something that we need to add to our notes if you didn't on Friday. Starts at 0, goes up, just counting numbers. Integers, abbreviated Z, positive and negative counting numbers. So we go in both directions here, all the negatives, 0, and the positives, counting numbers. Then we start adding decimals. If our decimal stops or our decimal repeats or it looks like a fraction, we call it a rational number, abbreviated Q. There are numbers that can be written as a fraction. Well, what kind of numbers can be written as a fraction? Decimals that stop and decimals that repeat. Irrational, which sometimes abbreviated RI, sometimes abbreviated IRR. Those will look like decimals that don't stop and don't repeat. Doesn't usually look like a decimal. Usually it'll look like a symbol like pi, square root of 5, okay? But if it looks like a decimal, it's all under that umbrella of real numbers, and that has the abbreviation of R. Now let's talk about what of these we really want to know today. Today, for what we are using, we're going to want to know something to describe things with decimals, which we will use real numbers, and without decimals, and we will use integers. Okay, so it's gonna fall into one of those two categories today, a real number, or more specifically without decimals, an integer. If you want to get more specific than that, every now and then you could narrow it down to a natural whole. You can. You don't have to. Okay. So the other thing we're going to need to be able to do we're building up to doing what's called writing our set and set builder notation. We have to be able to look at a list of numbers, a pattern, and use an inequality to describe that. So if you have a list of numbers, here's an easy way to go from that to an inequality. What I want you to do is you're going to write down a variable. I'll always use x. Write down the first number, and our first number is -5. And then you're just going to tell me which direction they are headed. Well, look at the pattern. -5, -4, -3, -2, -1. If I kept going, it'd be 0, 1, 2. We're getting bigger, right? So that's exactly what I say. X is getting bigger than -5. But because we'll always start with the first number, you always need to put that or equal to underneath. So try the second one. 10, 9, 8, 7, 6, ... Write that as an inequality. Use a variable, use the first number, and describe which direction it's going. 10, 9, 8, 7, 6 is getting smaller, so I'd say less than or equal to. Questions? Okay, bonus on this one, because I realize I don't have an example of this later. What if it doesn't have the ... Okay, what if my set looks something like 1, 2, 3, 4, stop, no ... Okay, it is treated differently. If there is no ... we don't use a single inequality, we use a compound inequality. So no ... right? We will use the first number, we will use the last number, we'll put a variable between them. And then our inequalities are always going to point to the left or be less than. So 1 is less than or equal to x is less than or equal to 4. So that's how I will write my inequality if it is no ... Questions on any of that? Okay, we have one more special case, and our special case is when it has a phrase multiples. If it says that we want a multiple of a number, first of all, you'll notice that we change it from an inequality to an equation. This is a special case. We don't see it often, but enough that I need to show you how to do it. If I want to write an equation that describes multiples of 3, again, I start with x, but this time it's going to be equals. You're going to use whatever number we're supposed to be multiples of, and then you're going to put another variable after it to represent any number times 3 would give me a multiple of 3. Questions? Okay. Putting those things together, identifying different sets of numbers, and then how to write an equation or inequality to describe a set of numbers, we're going to be able to write what's called a set builder notation. Today you're going to learn two types of notation, set builder and interval. Interval is nicer, cleaner, faster, and limited. Set builder takes a little bit more, but it works for everything. So unlimited and what we can use it for. So that's why we have to know it. So set builder notation. The first three symbols you see up here will always be there. Curly bracket, X, bar. We would read that all X's such that. The next part that is underlined in purple up here on my board is something that you need to fill in. That becomes specific to whatever set of numbers they hand you in the problem. Okay, so those sets of numbers that we were just writing inequalities for, that inequality, this is the spot where it gets written. After your inequality or your equation, you put a comma, an X, and that existence or that element symbol, right? And the last little spot is filled in with the set of numbers where X comes from. Now, we have a whole page full of numbers, natural, integer, whole, rational, irrational, real. I'm going to look for 2 there. You are going to put it into one of 2 options. You either going to call it a real number, and you're going to pick real numbers if it includes decimals, or you're going to put an integer there, and that is if there would be no decimals in that set of numbers. Again, that spot, if we look very closely, there is a rare case where maybe we would put something like natural or whole there. I just need you to pick from real or integer. And if the book says whole, integer would be fine there as well. Okay? So let's see this in action. If I hand you the set of numbers 5, 4, 3, 2, ... To write the set builder notation, again, the first 3 marks I make will never change. Curly bracket, X, bar. All X's such that. The next part that we fill in is going to be specific to the set of numbers. So 5, 4, 3, 2, this is why we practiced what we did earlier. I'm going to now write an inequality that describes the set of numbers. Okay, well, remember you use X and the first number in our set and decide if it's getting bigger or smaller, right? So X and 5. And as we look at these numbers, I see that X is getting smaller than 5, right? So I would say X is less than or equal to 5. Comma. X exists in. The only other thing we have to make a decision on is this. Are we going to use real or integer? If I continue that pattern, 5, 4, 3, 2, 1, 0, -1, -2, am I ever going to say a decimal? No. So if I'm never going to say a decimal, we use integers. Because integer says no decimals, says just counting numbers. Questions? I only today have one of each type of example. So if something about that does not make sense, I don't have a second example of that. You got to stop me now. Stop me at each individual example if something doesn't make sense, because you're not going to see it repeated. Each example I have is something different. So for example, what's different about this one? No ... right? If we want to be non-mathematical words about it, there is no ... right? But we know how to write this. We know, we already practiced that at the beginning. That was kind of my bonus example. I know the first 3 symbols, curly bracket, X bar, all X's such that. And if you go back to the one we did at the beginning, if there are no ... remember we now have to write a compound inequality, right? In my compound inequality, I know the first number and I know the last number because it does not continue on. So we start with 2 and 7 as our first and last number, and we put an x in the middle. 2 and 7 because that's the first and last number in my set. We know that it's going to be getting bigger as it goes, so 2 is less than or equal to x is less than or equal to 7. Comma, x exists in, and then we fill in that last one with either r for real numbers or z for integers, and the question is, are there decimals in this set? No decimals, right? I literally can see every number in this set. There are no decimals, and if there are no decimals, I say integers. Good with our no dot 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 problems. Okay, next one, starts as an inequality. That's new. We've always had to figure that out, but this one starts as an inequality. So that's what's different about this one. Guys, these are the easy ones. The one that starts as an inequality, all I have to do is literally copy the inequality in where the inequality goes. I don't have to do any thought process there. So you're going to be happy for this one for 2 reasons. First of all, you just get to copy the inequality. We don't have to think about it. And if it starts as an inequality, the set of numbers will become automatic. Think about numbers that are bigger than negative 17. Could a decimal number be bigger than negative 17? Like 10.5? 10.5 is bigger than negative 17, isn't it? So if it includes decimals, what set of numbers are we in? R, reals. So if it starts as an inequality, this is automatic. Automatically, it'll be the set of real numbers if our problem starts out as an inequality, always. Okay? Inequality, we don't have to think about what it is. We just copy it and make it from the real numbers. Last one, the multiples. This one has a couple weird ones that are individual to this type. So again, kind of highlight for yourself where it's different. First 3 symbols will never change. We practice the multiples. This is the only time that we're going to have an equation instead of an inequality. So remember a couple slides ago when we did this, it's going to say x equals. We use this number right here, 7, and then we add in another variable, n. That is what's going to be very different on this next step. Usually it says x exists in, but now I need it to say n exists in. Because when I plug in for n, it'll automatically fix x for me. Now, if I'm talking multiples of 7, will those have decimals in them? No. Think about your times tables, right? They don't have decimals in them, do they? So multiples of 7 are not going to be decimals, and if they're not decimals, they are in the set of integers. Any questions on any type of set builder notation that we've seen? I think I've kind of hit all the different varieties you're going to see. You just got to match up to what it looks like up there, okay? The only thing is there's a couple different varieties of starting out as an inequality. It doesn't matter if it starts out as this type of inequality or if it were to start out as like an inequality that was something like, let's say, negative 3 is less than or equal to 5 is less than 4. Or not 5, but x. Again, you would copy it here in its real numbers. Or if it was an or inequality, like x is less than 2 or x is greater than 10, you would copy that here, and it's the set of real numbers. Okay, so anytime it starts out as an inequality, you just copy the inequality, whatever formatting it's in. Got it? All right. After set builder, we have this other option that's called interval notation. Interval notation is way less work. It is less things to write, more efficient. It only works for real numbers. So if you go back to the 4 examples we just did, 3 out of the 4 were integers, would not work for interval notation. So that's why we have to have a second option for those other ones that come about. You'll see I have that noted real big here. It only works if we're talking a set of real numbers. What is it going to look like? It's going to look like an ordered pair, number, comma, number. That's all there is to it, number, comma, number. Smallest number has to be listed first. Biggest number has to be listed second. You'll notice I have 2 symbols on each end, a parentheses and a bracket. Well, we have to make the decision on what are we going to put there, a parentheses or a bracket. The right and the left end are completely separate from each other. So when would we use a bracket? We're going to use a bracket if we include that endpoint. We include an endpoint if the symbol there is a less than or equal to or greater than or equal to. The or equal to is what makes us include the bracket. Okay? Or equal to is why I would put a bracket next to something. So here's an example of me putting a bracket there. Smallest number in this set would be 3. Biggest number in this set would be 6. It says or equal to next to the 3. It says or equal to next to the 6. So I put brackets there. When would I use parentheses? If it doesn't include the endpoint, that would be just a less than or just a greater than. Here's an example. Same two numbers, but they change the symbol next to them. Not included. Means it gets really close to 3, but it doesn't actually get to be 3. This is when it's compound inequalities. Compound inequalities meaning I have two numbers. If I only have one number in my inequality, we will also use an infinity. It will be used when the set is unbounded. So that would be when it is not a compound inequality or there's just a single inequality. Whatever you want to write there so it makes sense. It's a single inequality, will include an infinity. So let me give you some hints here. It will be an infinity, either a positive or negative, because order matters. A lot of times the infinity will get flipped to the wrong place when we're doing this. Think about the number line. I use number lines in here a lot. On a number line, we would go from negative infinity up to positive infinity. If I were to draw myself a picture of x is greater than 6, I would put 6 on the number line. You guys probably did this back in like Algebra 1, pre-algebra, is I would have a dot at 6 and shade in the direction that it says I'm supposed to be going. So that would be an open dot at 6, shaded towards infinity. Okay, well the way that I shade is my interval notation. You can see right here, there's my interval, 6, comma, infinity, right? It'll be in the correct order on your number line. The other note I want to make on this is when you use an infinity, there is no thought process right here. Infinity is always a parentheses. Always, always, always. It doesn't matter. If I went back and changed this problem to an or equal to, the 6 would get a bracket, and I would not change what's by the infinity. It would still be a parentheses. You never have to think about a infinity. It's always parentheses. And remember, the two ends of this do not have to match. One can be a bracket, one can be a parentheses. Any questions? Okay, let's practice a couple different varieties of those. Given a compound inequality, we know the starting and ending number. So a compound inequality, you have two numbers in your interval notation. Compound inequality means I'll have two numbers in my interval notation. Tells me my smallest number, tells me my biggest number. I just have to decide on parentheses or brackets, and again, it is this symbol right here. Now, they are individual, so I look at the -2 first. It does have that or equal to, so I put a bracket. I look next to the 12. It also has an or equal to, so I would also put a bracket on that side. Decisions are made separately. They do not have to match. If it is a single inequality, that means I will have one number and an infinity, positive or negative. Kind of depends on which way the numbers are headed. If you need help, draw yourself a number line. Bigger than -4 would head this way, and again, the order that it's listed, there's your interval notation. -4, comma, infinity. Always a parentheses at the infinity. I don't even have to think about it. Use this sign right here to help me with the sign next to the -4. Greater than is a parentheses, not included. All right, last one we have not seen before. We've got an OR inequality. It is a compound inequality, but it's an OR inequality. On the OR inequalities, you basically do this like two separate problems, and you union the answers. On Friday, we learned what this symbol was, union. It meant to put together two sets. And so that's what we're going to use when it is the word OR, union the two together. So we just ignore part of it, and we just write an interval to describe x is less than 3. This is a great one for us to look at. Again, as we look at the order that those should be written in, less than 3 would head this way. That is the order that I write my interval. Negative infinity, comma, 3. The smallest number would be negative infinity. And again, an infinity is automatically a parentheses. Look next to the 3 to decide. And it is just a less than, so a parentheses next to the 3. Then I do the other one. Okay. Greater than 54, numbers bigger than 54 would head this way. There's my interval, 54 comma infinity. Automatically a parentheses at the infinity. Because of the or equal to, I would put a bracket at the 54. And then this is what's new. Give it another color here, or. Or shows up between my two answers as a union symbol. I am using number lines as a tool to help us see that visually. 100% optional. You do not need, I do not need to see them on your homework or anything, but if they help, use them, okay? Or visualize them or whatever it is. But a lot of times, this right here specifically, the negative infinity comma 3, gets flipped around a lot. So make sure that we're getting the negative infinity is always going to be your smallest number. All right? Okay, shifting gears. Oh, no. First of all, practicing. These are the directions you guys are going to see today. Let's talk about those directions. Describe each set in set builder and interval notation. So those two different styles that we just learned. If possible. Let's talk about that phrase right there. If possible. Okay, this is only possible if it is the set of real numbers. So if you decide in your set builder that it's coming from the set of real numbers, right, we will have both set builder and interval notation. If in your set builder you decide that it's coming from the integers, you will have set builder only, and under interval notation you would write not possible. So I will give you some time. You may work with your table, look back at your notes, write the set builder and interval notation if possible for those two different sets. When you get done, go ahead and check with your tables. Make sure, or if you have questions, check with your table. Use each other's help. Okay, so we had to rewind a couple pages to see our set builder. So going back to our set builder, same three symbols to start every time, curly bracket, X bar. We talked about that if it starts as an inequality, I now just take that inequality and copy it into my set builder. So it started out as X is greater than or equal to 50. I just copy in X is greater than or equal to 50. If it starts out as an inequality, it helps me with my thought process. Is there a decimal that's bigger than 50? Yeah, 55.7, right, is bigger than 50. So X exists in the real numbers. Now, what I had listed up here says if it is in the real numbers, I can write it in set builder, always, and I can write it in interval notation. So because this says real numbers, I can do the interval notation. It is all based off of that symbol right there, real numbers. So my interval notation, smallest number in this set up to the biggest number in this set. If I need to visualize this set, I'm going to use a number line. Here's 50, greater than or equal to. Numbers bigger than 50 would be over here. There's my interval. 50 up to infinity, always parentheses and infinity, and then I make my decision. Or equal to tells me to bracket the 50, include it. Any questions on that first one? Second one, again, it doesn't matter what type of set I'm looking at, I can always write set builder, all X's such that. This time I have to figure out what the inequality is because it's a list of numbers. So if I'm figuring out the inequality, I use X, I use the first number, and I look at which direction it's headed. X is getting smaller than 5, so I would say less than or equal to 5. As I think about that set of numbers and where it would continue, I see that if I followed that pattern, I would never say a decimal. And if I'm not going to say a decimal, I call it an integer. And that also reminds me that if it's in the integers, I can only do set builder. So because I said integer right here, that tells me that my interval notation is not possible. Any questions on that? All right. Now shifting gears a little bit. It's still about functions. This is a little bit of review. At some point over your math career, you have seen all of these individual pieces, kind of putting them all together. When is something a function? First of all, a function is a relation that assigns exactly one value in the range, which is your y values, to each value of the domain, which is your x values. So a couple different formats that we can see that in. One of the ways that we can list x and y values is like a table. If I were looking at a table, this would be my x's, this would be my y's, and basically what I'm looking at is I can only have one arrow out of the x's. The y's make no difference. I can have as many arrows as I want coming to the same number, but I can only have one arrow coming out of the x's. Second way that I could see that would be that same set of numbers as an ordered pair. Okay. What am I looking for if it's an ordered pair? I would look for a duplicate x. And it needs to go to different y's. Okay, so for example, if I had added to this set 1, 7, that would be duplicate x's going to different y's. That would make it not a function. So to be a function, I can only have, maybe I should say no duplicate x's. Function notation. Function notation is this fancy math speak. It's an f and a parentheses x, read f of x. It replaces from Algebra 1 where we used to say y. Y equals 2x plus 1 and f of x are the same thing, y and f of x. So why the difference? Well, last year you guys did a whole section called conic sections. You remember those? Hyperbolas, ellipses, circles, all of that. All of those had equations. They are not functions. And we're going to bring that back up here in a couple minutes. You would never have been able to write any of those as f of x. The only ones that we can are the ones that pass all of these tests, meaning that They only have one x for each y. So other ways that we can identify things as a function. Visually, what if I don't know what the numbers are, but I have a picture to look at? We use what's called our vertical line test. Your vertical line test literally just draws vertical lines through your picture. And if I hit my graph at more than 1 point, it fails. If it only hits my graph at 1 point each time I draw a vertical line, it passes. So let's look at some examples of things that pass and fail. Parabola, does that pass our vertical line test? Yeah, that's a function, okay? This next one, does that pass our vertical line test? No, this fails. Draw a vertical line fails because that single line hits my graph at more than 1 point. That would not be a function. Those are pretty obvious. I threw this last one on here just so we can have a discussion about it. When we're looking at a piecewise graph, you really just need to be cautious where they overlap. Remember that closed dots and open dots really do mean something, right? It means that it gets really close to this, but it doesn't actually include that point. So is this right now passing the vertical line test? Yeah, although it kind of looks like it hits there, it's not actually hitting anything, right? So it only hits my graph down here. If they were trying to be tricky and like fill that in, now it fails, doesn't it? So this would not be a function. That is a function, right? So just be cautious that where piecewise functions overlap, that one of those is a open dot or it would fail your vertical line test. Other formats that we might be asked to identify whether or not something is a function, a story. Okay, and really it's kind of, does the x have any impact on what the y value is going to be? Let me give you an example here. The input value x is the height of a student in inches. The output value y is the number of books that the student owns. Okay, so let me give you a very obvious example here. So our x is our height in inches, our y is our number of books. I'm going to use myself and hopefully somebody in here. I'm about 6 feet tall. Okay, so 72 inches. Is anyone else in the room about 6 feet tall? Can be 6 feet tall. Perfect. So there's 2 of us in here that are 6 feet tall, 72 inches. How many books you got with you today? 2? Okay, so she's got 2 books. 7 inches tall, 2 books. I'm 72 inches tall. If I were to count up how many books I have, I mean, that cupboard back there is stuffed full of pre-calc books. Let's say 100. Is this a function? No, same x value going to 2 different y values, right? Does your height have any impact on how many books you're going to have? No, not a function, okay? So if you're having trouble reading a story and deciding whether something is a function, try to think of it maybe in a table or something like that. Can I come up with 2 things in the x that would go to different y values? We already looked at this, but I just want to show it a second time because they try to trick you because they wrote it more than once. Do you see how it has the same x value here and it goes to 2 different y values? Is this a function? No. Okay. Now if I were to change it, and I don't know why they would ever list it like this, but just to be clear, would that now be a function? If it's the same exact point twice, it doesn't count as 2 different points. That would technically be a function. I don't know why they would ever list them twice, but that technically would be a function because it'd be the exact same point, not 2 different points. Okay. But that, not a function, okay? The next one we've already seen. We already talked about a parabola. It is a function, so if we have a graph, we look at our vertical line test. The letter D is what I definitely want to talk about. What happens when it is an equation? Okay, things are going to be a function unless we run into this very specific thing in an equation, and that is going to be if we ever run into a y squared. When we run into a y squared, the result is not going to be a function. Now, that is not the only one out there that would ever not be a function, but for anything we're ever going to see, that's all you're looking for. An x squared is fine, right? We saw an x, this is an x squared, totally a function. Y squared, not a function. Go back to those conic sections. Didn't all of those ellipses and hyperbolas and circles all have a y squared somewhere in their formula for the equation? None of those are functions, right? So y squared is the key to make an equation, not a function. Any questions? All right. Last couple things are just some algebra reminders that I want to make sure that we have. This very first part, I sure as heck hope you can do without me explaining, and that is if I handed you f of x equals x squared minus 2x minus 8 and asked you to do f of 3, you would know what to do. What would we do? Plug in 3, okay? So we got the basics. I just want to hit some quick algebra reminders on this, and that is this. What if I have something that's a variable? Well, I still just sub it in for all of my x's. And if I have a variable, I'll have a variable in the answer. We're just going to clean it up. So the one reminder I want on this first one is this. When I have a monomial squared, first of all, a negative squared always is positive. Don't listen to your calculators unless you really know how to type things in the right way. Your calculator might tell you that negative 3 squared is negative 9, but you didn't type it in right. Your calculator can only do so much, right? So just make sure that we get that correct and we square both parts. Remember, a negative times a negative is a positive. That is as far as you are going to take that problem. Some people do it. Do I need to factor? No. No. Just clean it up, combine like terms. That's all you're doing. The algebra reminder I need to give you on this last one. What if I plug in a binomial? Again, we've got a variable to start with. We're going to have a variable in our answer, and we're going to clean it up as best we can. All right, help me out algebraically. This part right here, binomial squared, what do I have to do? Thank you. FOIL. I have to write that twice in FOIL. And here I've got to distribute, get that negative all the way through if you've got a problem like that, right? So when I write this twice in FOIL, let's go real fast here. 4a squared minus 2a plus 1. Distribute that negative 2 through, we get negative 4a plus 2 minus 8. That I need to clean up because we have like terms throughout there, so I would want to find all my like terms and put them together. So cleaning this one up, I only have one that's got a squared, so that's by itself. Negative 2, negative 4 would be negative 8a. 1 plus 2 minus 8 would be negative 5. Yeah, negative 5. Clean it up, that's all we can do. Any questions on that? Okay, last thing. People make this way harder than it's supposed to be. When it says f of x, right? Look at that letter. That is x. That is x. So if I were to think about my ordered pair, it goes x comma y. That is the x number. They're asking you in this question, if I were to look at this graph, what would be the y number for 1 comma something? So look at the graph. 1 comma, my graph is way up here. Wouldn't it be 1 comma 4? My answer is the y value, 4. Finish that other ordered pair. Negative 3 comma, look at your graph. What would it be? What do you think? 0. Negative 3 comma 0. So our answer would be 0. Any questions on that? All right, guys, your assignment is on page 9, regular 9, not P9, right? Page 9, you're doing 2 through 30 evens, skipping number 10, 31, and 38.